Okay, so one more time. So so we have it on camera. What does it mean to be isomorphic?
Well, it just occurred to me there's a bijection.
It's a bijection.
Yes.
Okay.
Such that every point can map to another point that has the same neighborhood. So it, I'm sorry, the degree sequence is the same, and
okay, so let me write down some things. So I wasn't here last Thursday. I wasn't here last Thursday. So let me start with. So I heard some words that I want to review. So degree sequence.
yeah.
So what's a degree sequence?
It's the list of all the degrees are in a graph. Such as, like, if it said 1 to the 4th, that would mean there would be 4 vertices with degree 1.
Okay. Okay, so one way, of course, if you have a graph of order n, one way to list the degree sequence would be to actually list the degrees of all the vertices. Okay, and or we could list them as IDIs for I equal to 0 to n minus 1. We can't have any vertices of degree more than n minus 1, right? So this would be I vertices of degree I. We could write it like that. Okay, so that's the degree sequence. Is that all we need for two graphs to be isomorphic?
No, when you map one vertex to another vertex, it has to have the same adjacencies.
I think so. So can you give me an example of two graphs that are isomorphic and an example of two graphs that aren't isomorphic? And I would prefer two graphs that had the same degree sequence that aren't isomorphic.
Do you want me to draw it?
Okay. Do you want to draw it, or do you want to tell me? I mean, is it huge?
It's just 4 vertices.
4 vertices. Okay, wait a second. I can draw for 4 vertices. 4 vertices.
So just draw a square.
Okay.
Yeah, so they all have degree 2.
Okay.
And then to another vertex.
To another.
No, I'm doing a separate graph.
A new graph. Okay. New graph on 4 vertices.
Yes. Connected diagonals with no middle vertex. And then draw 2 vertical lines. Yeah.
Okay, so let's slow down. The degree sequence of this graph.
Is 2 to the 4th.
Yeah. 2. I understand 2 to the 4th. 2. And the degree sequence of this one.
2.
Okay. Are these isomorphic?
Yeah. Yes.
Oh, they are isomorphic. Okay. Yeah. So the mapping is pretty obvious, right? Right. We can just twist it around. So these are isomorphic. Can you give me a graph on 4 vertices with degree sequence 2 that's not isomorphic to this?
Given enough time, I could produce it for you.
No, I don't think you could. I don't think you could. I think there's only one graph on 4 vertices.
Would it just be a disconnected graph?
So okay. If you let me do this like that.
Sure.
Yeah, I don't like multiple edges. I want a graph. I don't want a multigraph. Right? If you allow multigraphs, let's make it clear, if I allow multigraphs, then these two multigraphs, it's multi because it's only got one, but it's still be considered a multigraph. This is clearly a multigraph because it's got 2 edges between these points. The degree sequence here is 2, 2, 2, 2, and the degree sequence here is 2, 2, 2, 2, and they're clearly not isomorphic. Okay, that's for sure. Okay, so can you give me one that's what about like these two? And I may be going over more of what Michael did last Thursday. What about these two? Degree sequence 2, 2, 2, 2, 2. for both of them. And so they're isomorphic. Is that enough? But to convince me that they're isomorphic, you'd have to do what? Find a bijection. Can you all see this? This board is awful. Okay, so you need to find a bijection. Sometimes a bijection is not so easy, but so let's map that vertex to that vertex. Then these two vertices would have to be mapped to which two?
The vertices are adjacent to the one that just got mapped to.
Okay, so this goes here and here. And now let's see. So now we have to map these two to these two, and it does matter, I think. Let's see. I can't map this one here because it's adjacent to this vertex. So I'll map this here and that there. So they're isomorphic. Is that clear? I mean, you need to convince yourself that I've got a isomorphism between these two graphs. Let me go one step further. My favorite graph, it's not really my favorite graph. Okay, what's this called?
Peterson graph.
The Peterson graph. Okay, and we'll, at some point later we'll see Peterson will come into some of our studies, and this graph has some interesting features. It's 3 regular, and it looks like there's a 5 cycle out here, and there's a 5 cycle out here. 5 cycle in here. Let's make sure. 1, 2, 3, 4, 5. Back to start. Okay, so the 5 cycle. It's 3. The degree sequence is 3, 3, 3, 3, 3, 10 threes. Mm-hmm. Okay, what about this one? Let's see. I sort of argued there's 2 5 cycles in the Peterson graph. There's 2 5 cycles. Sorry, I'm going to come back over here so they at home can see the board. Okay, there are 2 5 cycles. Here's a 5 cycle. Here's a 5 cycle. Here's an outside 5 cycle. Outside 5 cycle, and the inner 5 cycle is matched up with the outer 5 cycle. What do you think? Can someone give me a reason why they're going like this or why they're going like that? Vote. Isomorphic. They kind of look similar. I drew them similarly. It's 2 5 cycles and 5 edges. Anybody? They're 3 regular. Do we know what all? And if I say a word, if I say something that I haven't defined yet, tell me, because sometimes I forget where we are in the book. 3 regular, 2 5 cycles. The points in the outside 5 cycle are matched up with the points on the inside 5 cycle. Anybody? Okay, so what I would like you to do is draw these 2 graphs on your paper. Everybody got them? And then spend some time with these two graphs over the next several days, because you're going to be snowed in after today. If we're snowed in, if school's closed, then we don't have school class. But I would doubt that's the case. You could hope. Okay, so again, the question is, are those 2 isomorphic? By the way, on page, where is it? You know what I'm looking for? I'm looking for, it's in chapter 2.
Yeah, chapter 2.
Oh, there it is. Okay, on page 58. It's in the 50s. Okay, right in the middle of page 58. And you're going to stop me if Michael did this last Thursday. And again, I do apologize for not being here. I have some travel that I needed to get done. Okay. So if you look at page 58, notice A looks like this one, and B, that's really strange. I can't even describe that. B doesn't look like this one. And in my book, I drew this one in my book in between. So the question is, just like the question asks, determine if the following two graphs are isomorphic. So you may want to look at A and B, and then decide about C, which is this one. Okay. Any thoughts? Okay. Okay, so let's vote. They're isomorphic. No, one more time. This one and this one are isomorphic. They are not isomorphic. But I don't know why. Okay, all right, okay. So we'll come back to... so let's see. By the way, there's homework that I assigned that was due... That's due a week from today. And it includes, by the way, page 59, number 10. Construct two non-isomorphic three regular graphs of order 10. Maybe they're all isomorphic. Well, then that problem would be very hard. Okay, but so not only construct them, but I want you to be sure you tell me why or how they're not isomorphic. The degree sequences are clearly the same. Okay, all threes, 10 threes, the three regular, but hopefully they won't be the same, or you'll find out why they're not the same. Okay, and you didn't do subgraphs last week, right? Okay, so just like you did when you were studying sets in, I don't know, 6th grade or something like that. Okay, so we have we still have a graph, and we have some edges. So graph is made up of an edge set and a vertex set. Then we talk about a subgraph. A subgraph of G would be a subgraph of G, say H, would have a vertex set of H being a subset of the vertex set of G, and the edge set of H being a subset of the edge set of G. And now what we're gonna want to know is, when do we have subgraphs of certain types? And one type in particular that we'll be interested is what it means to be an induced subgraph. And I'm going to go through several definitions, and then we'll go through some examples. Okay, so an induced subgraph has so H is an induced subgraph of G. H is an induced subgraph of G. If V of H, the vertex set of H, is a subset of the vertex set of G, and all the edges of G are the edges of H. Okay, so let's go back to the Peterson graph for a moment. Let's label these 1, 2, 3, 4, 5, and then A, B, C, D, E. I just did that just for the heck of it. So I have my 10 vertices labeled. So the induced subgraph on 1, 2, 3, 4, 5 is going to simply be, that's pretty simple, is that. So it includes all the vertices 1, 2, 3, 4, 5, and all of the edges between those 5 points. So that's an induced subgraph. Just to show you what a non-induced subgraph would be, this is a subgraph of the Peterson graph. This is a subgraph of this Peterson graph, but it's not an induced subgraph. Okay, is that clear? Okay, so you really want to be, I can't encourage you enough to draw lots of graphs, lots of little graphs, and I've never had a student that told me they ran out of graphs, because if you remember last week, how's that atlas doing?
It's good.
Okay, so the atlas of graphs says that like on 10 points, there's a lot of different graphs. I forget what the number was, but it's pretty large. Okay, so you always have lots of graphs that you can look at, and you should be playing with lots of these graphs. So what I want you to do is I want to go to page 60 and 61. Okay, so we're going to spend a few minutes on this. So I have how many? I have 7 graphs. G, and then H1, H2, H3, H4, H5, and H6. Okay, so it says that H1 is not a subgraph of G. Because notice is not a subgraph of G because if I look at the vertices A, X, Y, and Z, A, X, Y, and Z, those 4 points in G do not have A and Z adjacent. Okay. So when I label the vertices, this subgraph A, hold on, A, X, Y, and Z is not a subgraph. But I'm going to ask a question. Is K4, remind me what K4 is. What's K4? No. This. What's this? That means cycle. Okay, in this graph that means cycle. Okay, and K4 is just 3 edges? All of the edges. It has all the possible pairs. So K4 is better known as the complete graph. And it doesn't matter how I draw it. You can draw it like this. Right? The drawing isn't what's important. I can draw it like this. Just to be crazy. There's another drawing. Oh, there. Okay, you don't have to draw straight lines. Notice each of these are K4s. Each of these are K4s. Every pair of points are joined by an edge. But when I label the vertices, and I look at A, X, Y, and Z, in my original graph G, what does the graph on A, X, Y, and Z look like? Now look carefully. A, X, Y, and Z. What does it look like in my original graph G? It looks like this. But H1 doesn't look like that. Is that right? I don't believe there's an edge from Z to A. If I had the edge from Z to A, then in fact all of the 6 edges in H1 would be contained in G, and H1 would be a subgraph of G. Now, let me make it clear, K4, if I drop the H and I don't look at labeled vertices, K4 is a subgraph of G. Can you tell me? I believe that's the case. A, B, X, and Y. Notice A, B, X, and Y form a K4. So depending on how I use the particular terminology, if I pick a graph H, which is H1, which is under part B, and I specifically say these 4 vertices and these 6 edges, these 4 vertices and these 6 edges, they're not the same in the graph G. Okay, so when I label the graph H1, that is not a subgraph of G. Is that clear? Okay, but K4, when I just throw it out there as K4 being a complete graph on 4 vertices, K4 is a subgraph of G, and that would fall under A, B, X, and Y. Okay? All right. So now what I want you to do is H1 is okay. So H2 through H6 are subgraphs, and we'll talk about proper in a second. Are subgraphs of G. Is that true? Can you? Of course, they're labeled, right? A, B, Z, Y. A, B, Z, and Y form a 4 cycle. A goes to B, B goes to Z, Z goes to Y, and Y goes to A. And in fact, the question I want to ask is it an induced subgraph? Is the graph that they have written down in part C, H2, is H2 an induced? One more time. Is H2 a subgraph of G?
Yes.
Yes. Right? All the edges in H2 are edges in G. Is H2 an induced subgraph of G? So induced means that it contains all of the edges. Induced subgraph means that it contains all of the edges of G on those vertices. On those vertices. And we're gonna talk a little bit more about what it means to be induced. Okay? So is this an induced subgraph? No, because
B is not connected to Y.
no. Yeah, okay. In the subgraph, B is not connected. In C, in H2, B is not connected to Y. So it's not an induced subgraph, but it is a subgraph. Is it clear what the difference between induced and not induced? Okay, what about H3? So the question I want you to, on your tables, H3, H4, H5, and H6, are they subgraphs and are they induced subgraphs? Talk amongst your table guys.
Wait, well, they're all subgraphs, right?
They're all
established that. So H3 isn't induced because the UV edge isn't there. X and YB again. Oh, yeah.
You have no one to talk to on your table. You can go here.
H4 is an induced subgraph.
You have a question?
Looks like
Okay, all right. So Ying's asked a question. What's the difference between a subgraph and an induced subgraph? So someone tell me in their own terms what it means. What's the difference between just being a subgraph and being an induced subgraph? Which might you say is more restrictive? The induced subgraph. Okay, so what distinguishes between an induced subgraph and a subgraph? Okay, so more. Just any edges? But even more than more. Tell me more than more. Not just more. Has all the. Okay, so the most important part is to be an induced subgraph, okay, of the original graph, it must contain all the edges in the vertices in your subgraph. For example, which one were we just doing? H2 is a subgraph. It's a subset of the vertices of G, and it's a subset of the edges of G, but it doesn't contain BY. It doesn't contain the edge BY. Okay, one more time. H2 is a subgraph, but it's not an induced subgraph because it doesn't contain the edge BY. Okay, and it could be missing more than one edge, right? You can be missing many edges. And I'm gonna put it out there because it's gonna come up at some point. Okay, there is a subgraph of this Peterson graph. It is a subgraph. It's not an induced subgraph. And in fact, when we have no edges, we call this the empty graph. Okay, has no edges, but it is a subgraph. This is a subset of the vertices, and the set of edges in here is a subset of the edges in here, right? That's a vacuous statement when you have the empty graph. One more time, the edges in here is a subset of the edges that you have in here. Or, yeah, I guess this is the only one that I've labeled 1, 2, 3. Subset of edges in here or here. Okay, is that clear? So we're going to use sets just like you did in previously. Okay. All right, so that answers your question. Yeah. Okay. All right, so now you're still going through these six graphs and deciding which are subgraphs, which are induced subgraphs, and then we'll talk about which are proper subgraphs.
And then 6 is induced because it's in a bunch of stuff for A.
Yep. Yeah, they're pretty much all missing BY except for H4, which is the only induced subgraph.
Mm-hmm.
Yeah, so as multigraphs, yes. Okay, so when I say that H4,
Yeah.
oh no, there's only one edge between B and
If
C.
you go like 1A, E4, and you try and do that, the one on the left, you end up with 4 and 1 adjacent to each other.
Right.
I mean,
I feel like
you know,
you don't if you
yeah.
start labeling
So yeah, we'll
neighborhoods.
Right.
yeah, just like set theory.
So the
And I
edge
still,
side-
and I was thinking like how exactly would you go about proving
I mean,
that?
so
We
we
just
use
found
element of
a relation
no,
show that it's not bijection, but we still have to, to do a formal proof, we have to show that one doesn't exist.
Right.
So I was just thinking how one might use that.
Yeah, because the BT is like go through every possible
Right,
path
right.
and show that none of them work.
Yeah, and you could cut it down by 5, because you can make a symmetry argument. You don't have to
Yeah.
keep rotating it over. But yeah, it's like I wonder if you could just like start at the top one, move to the one under that, and then move to the next two, and then move to the next two after that, and just show that they're not the same. I wonder if that works, or if I just once again found a function that is not a bijection.
Right. Disproving is much more of a pain.
Right. Yeah, I guess started on homework. I did the one with the 2 10s, but then I was thinking it would probably be easier realized if I just made this just 2 disconnecting ones. I could just make like 4 and 6, 3 regular, or yeah, just more clear. It's not too bad. There was I'm almost done. I knocked it off last night in a couple hours. There was one about 90% of the way through it, and I figured out I was proving something lower than what it was asking me to prove. So I've got some work to do on that one. But then the rest of it is just like I want to have a look at it and make sure like do I see it? Those kinds of questions.
Right. Well, I've got like a real analysis class right now, which you get through the proofs and think, okay, that makes sense to me, and then you get it back afterwards for review, and you just realize you weren't nearly precise enough.
Yeah. Yeah, this first one was, does there exist a 3 regular graph with 8 vertices, a 3 regular graph with 9 vertices?
Okay, so we're looking at H2 through H6. H2, so one more time, H1 is not a subgraph, but in fact it says it up here. H2 through H6 are subgraphs. And then there's something in the parentheses that we'll talk about in a second. So is that clear that these are subgraphs? And they don't have to look the same. Notice in H2 we've drawn them geometrically the same. But the geometry makes no difference. So I could draw it as just a square. It is a 4-cycle. It's just a square. That's fine. I could put the points however I want. So I could have drawn it like this. The geometry doesn't matter here. We're not worrying about the geometry. Okay, so H2, notice he tries to give you the exact edges as they are in G. But that's not necessary. The only thing that really matters is that in H2, the edges AB, BZ, ZY, and YA are in the graph. Okay, so H2 is a subgraph. In fact, all of them are subgraphs. All of them except for H1. Okay, is that clear? Mm-hmm. Okay, so let's see. I want to, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so let's look at special one is H5. H5 has the vertex set of G is equal to the vertex set of H5. In that case, we call the subgraph H5 a spanning subgraph. So it spans all the vertices of G. Spans all the vertices. A proper subgraph has the same set of vertices, but not all the edges. Okay, so a proper subgraph. They're all proper subgraphs, as long as it's a subgraph. So proper means that proper, G is a proper, sorry, H is a proper subgraph, of G if the edge set of H is not equal to the edge set of G. But it is a subgraph. But H is a subgraph. So it's not all of G. That's what we mean by proper. It's like what we would mean a proper subset has that same definition. That you have a set, and then a proper subset is a subset that is not equal to that set. So we're using the same sort of notation as we did in set theory. Okay? Questions? Okay, we have a spanning subgraph. A spanning subgraph means that the vertex set is equal to the vertex set. So as you can see, H5 has the same vertex set as G, so it is a spanning subgraph. Okay, it doesn't have to be connected. Doesn't have to be connected. Of course, that's the only, let's see. Oh no. So if we look at, notice if we look at G, H6. H6 has all the vertices of G, A, B, X, Y, Z, V, U, A, B, X, Y, Z, V, U. So it is a proper subgraph because it doesn't contain all the edges. And it's also a spanning subgraph because the vertex set is equal to the vertex set of H6 is equal to the vertex set of G. So it's a spanning subgraph. Notice also H5 is a spanning subgraph, contains more edges. Doesn't matter how many edges it contains, it just has to have all the vertices. Okay? Questions about that?
I think the similarity between E of H and E of G.
Oh, this is a subset not equal to. Sorry. Did you not? Sorry. Is that not a standard? I could have made it up.
I've seen it a few different ways, so I don't think you made it up, but I also don't think it's standard.
Because I mean EH being EG without the line underneath, it just says that this is the edges of H are a subset of the edges of G. It doesn't say that it's not equal to the edges of G. So somehow we have to distinguish that. So I use this not equal to. Okay, there may be other ways. Okay.
And also, just to double check, a proper subgraph does not necessarily have to be a spanning subgraph.
Does not
correct?
necessarily
They're
have to be.
completely independent.
That's
Okay.
correct.
Cool, thanks.
Okay. Questions? Uh-huh. What? Yeah. So the way they define it in the book is that he does include that H has got to be a subgroup of G, right? So if you read the book, okay. So on page 60, a subgraph H of G is said to be proper if H is not isomorphic to G. So if they were isomorphic, they would contain all the edges. If H was isomorphic to G, then H would necessarily contain all the edges and all the vertices. To say that's another way of saying a proper. I mean, so the edge set of G is not edge set of H is not equal to the edge set of G. Now that's okay. So there is a little problem with that. Okay, let me just. So now I see why he's defined it like that. Okay, so let's look at this graph. That's enough. Okay, so let's call this X, V1, V2, V3, V4, V5. So the edge set of this is V1, V2, V2, V3, V3, V4, V4, V5, V5, V1. So that's the edge set. The vertex set is X, V1, V2, V3, V4, V5. Okay, in this book, they say that V1, V2, V3, V4, V5 is a proper subgraph of G. Is a proper subgraph of G. No, why not?
So H
So it's yeah, sorry. Yeah, sorry. Okay, so yeah. Okay, so they're using the fact that the vertex set or V of H is a proper subset of V of G. Sorry. Thank you. Okay, so in particular, it's proper if it is, and I'm going to use the word smaller than if H is smaller than G. Smaller meaning it can have fewer edges, it can have fewer vertices. Okay.
So would that mean for this graph?
For which one?
For this one?
Uh-huh.
All the subgraphs is the same.
All of the subgraphs are proper. They're all proper subgraphs of G.
Of G for this one.
For this one,
Okay.
right? For this, I'm pretty sure, if I'm not mistaken, on example 2.3.1, they're all proper subgraphs of G.
So what is the difference between the normal subgraph and the normal?
Okay, so we don't use the word normal. Okay, so the only one that's missing from proper is the graph itself, is the whole graph.
Mm-hmm.
So to say that G is a subgraph of G, literally that's true. Literally, the set of vertices and the set of edges are subsets of each other.
But it's not the proper.
It's not a proper subgraph.
Okay.
Okay?
So is that all the like a subgraph of G is the proper subgraph except the G itself?
Right, that's
Okay.
correct. Right. Okay? Okay, spanning we got, let's see.
It's like, yeah.
Okay, subgraph. Okay, so let's see. I've got proper. I've got spanning. I've got induced. I've got induced.
Okay.
So someone remind me what the difference between a subgraph and an induced subgraph is? Is every subgraph an induced subgraph? So can you give me an example? Can you give me an example of a subgraph here that's not induced? A subgraph of this Peterson's graph that's not induced. Wait a second. So, oh, I see. Yeah, okay. So, that? No edges. Okay, so this is a proper subgraph of the Peterson graph. Okay, and in fact, just to be clear, it doesn't have to contain all the vertices, right? Doesn't have to contain all the vertices. So this is also a proper subgraph. It's just a subgraph that's not the whole graph. That's what we mean by proper. Okay. So let me jump for a moment back to that Peterson graph. Where was that? Come on, I had it. Didn't I? Oh, there it is. On page 58, just look at the 2.2.7. Now, those two graphs certainly don't look like they're the same graph. At least I don't think so. So how might you go about showing that they're not the same graph? One more time. I'm not going to draw it because I'm not that good. Okay, so A is the Peterson graph like we've grown to love. And B is, let's see, it's a 9-cycle. Have we talked about cycles? Mm-hmm. Okay, so a 9-cycle. There's 9 vertices on the outside that make a little cycle. Mm-hmm. With a point in the middle that's adjacent to 1, 4, and 7, if they were labeled. Of course, they're not. And then there's some random edges. It looks like random edges. Okay, so can you give me some properties that are the same? Are there properties that are the same? Same number of vertices. They're both 3 regular. Anything else? So now, how would I show that those are either are isomorphic to each other, they're the same graph, or not? The easier one is to show, easier is not a good word, but to show that they're isomorphic, we would look at a mapping from the 10 points, which of course they're not labeled, the 10 points in A, and look at a mapping to the 10 points in B. It's good that they both have 10. And I have to show that that mapping preserves all the edges. And there are only 15 edges. I'll repeat that again. Only 15 edges. Yeah, it's actually a lot of edges. Okay? So, I mean, you might want to think about how you would actually show that A and B are isomorphic. And in fact, if you Google the Peterson graph, there's probably 10 fancy drawings of the Peterson graph. Different drawings of the Peterson graph that look kind of neat. But now my favorite. This is my favorite drawing. One more time. Okay, so there's an outside 5-cycle and an inside 5-cycle. I'm going to say it again. I'm going to ask the question again. Are those two isomorphic? This and the Peterson graph. Look, I got a 5-cycle on the outside, a 5-cycle on the inside, and then we're joined by edges. It's not. Yeah, so I want to do it now. Because I mean, so how do you tell when two graphs are not isomorphic? Well, we look at the degree sequence. If the degree sequence is the same, that's a pretty good indicator. What's the degree sequence of the Peterson graph?
3 regular.
10 threes. What's the sequence of degrees for this graph?
10 threes.
10 threes. They're probably isomorphic. So now you have to get more into what I might call the weeds of the graph and the structure of the graph. So let me give you the easiest way to see that these are not isomorphic. They're not isomorphic. So oh, look, I got it drawn right there. Okay. Take 1-2 minutes. Look at the Peterson graph as it's drawn here. find the smallest cycle that you can. Look for cycles in that graph. A cycle. You know what a cycle is. Do we know what a cycle is? Who knows what a cycle is? Okay, so help me out. What's a cycle?
It's like you connect all the edges and you don't I know what it is, I can't.
Yeah, that's the problem with graph theory. You know what it is, but you can't write it down. Okay, so a cycle is a sequence of vertices, x1, x2, x3, x4, x5, xn, so that x1 is adjacent to x2, x2 is adjacent to x3, x3 is adjacent to x4, and all the way around xn is adjacent to x1. That would be a cycle. Okay, what can you tell me about the cycles in the real Peterson graph? This is the real Peterson graph. What? How'd you know that?
Can't find one.
Okay, so this is an important observation. The smallest cycle in the Peterson graph is. Are there any 3 cycles?
No.
Are there any 4 cycles?
No.
Probably safe to say that. Are there any 5 cycles? Okay, there are 5 cycles. Those are easy to see. Let's go over here. Are there any 3 cycles? Are there any 4 cycles? Yes. Wait. There's a 4 cycle here. No 4 cycle here. Can the 2 graphs be the same? No. Okay, so that's one of the tools for showing that a graph is not. 2 graphs are not isomorphic. Okay, let me tease you a little bit more. What's the longest cycle in the Peterson graph? Let's just call it P for Peterson. Let me stop for a second. Is there a 3 cycle? Now, a 3 cycle would be pretty easy. A 3 cycle, you would look at a vertex and look at its 3 neighbors. It's 3 regulars, so 3 neighbors, and you want to try and find 2 of those neighbors that are adjacent. That's what you would need for a 3 cycle. And if you look at every vertex neighborhood is independent. Have we defined independent? No. Okay. That's coming. Okay. Every set of 3 vertices. Look at vertex 1. Vertex 1 is adjacent to 2, 5, and A. I'm looking at the Peterson graph. Notice 2 and 5, 5 and A and 2 are all non-adjacent. Okay, so there's no 3 cycles. There are no 4 cycles, and you can actually convince yourself of that. So the last one that I want to ask you about is in a graph, there's a very special form when you have a cycle that contains all the vertices. Okay, this is kind of special because we haven't spoken much about applications. And if we look at these graphs as roads or networks, or you can think of it as a computer network, maybe you want to start at some vertex and using either roads or wires in a computer, or you want to get all the way around and get back to where you started. That's a special cycle. So let me ask, can you find a cycle that has 10 vertices in the Peterson graph? You all shake your head pretty quickly. Anybody? No, we can't repeat it. Cycles don't have any repeated edges. Cycles doesn't, certainly they don't have any repeated. What's the definition of a cycle? It's a closed path. And a closed path has no repeated vertices. A path has no repeated vertices. Very good. Okay, so is there a closed path with all 10 vertices on it? All right, so that's, you can just sort of suffer through that tomorrow as your, tomorrow? Is it going to snow tomorrow? Tomorrow? Okay, so as you're stuck at home, you can draw the Peterson graph. Okay, questions? Okay, so we got induced, we got, okay, so I want to move on to page, hold on. So let's look at the exercise for section 2.3. We're not, okay, so he mentions it in the book. It's an interesting problem. It's an interesting problem that's been around for a long time. And, you know, when problems have been around for a long time and still aren't solved, I don't believe they belong in an elementary course or book. But it's in here. So it's something called the reconstruction theorem. Reconstruction problem. So I have imagine that I have a graph on n vertices. Imagine that I have a graph on n vertices. They're not labeled. They're not labeled. So here's a graph on 10 vertices. They're not labeled. And one by one, I'm going to remove exactly 1 point. So I'm going to give you n graphs, unlabeled, n graphs with order n minus 1. So one by one, I'm going to remove a vertex. So I give you this graph. Notice they're unlabeled. I'm going to give you this graph. Then I'm going to give you this graph. And then I'm going to give you this graph. And then I'm going to give you this graph and this graph. So I'm going to give you a list of, in this case, 10 subgraphs. Vertex deleted subgraphs. Okay? And I give you that list of 10. From that list of 10, can you always reconstruct the original graph? And this has been a problem that's been around for 100 years. And it's not known. There's a lot of graphs. You know, maybe we know the answer for all graphs on up to maybe in the 20s. Maybe we know the reconstruction problem for all graphs up to 20 or 30 vertices. But that's just denting the surface. Okay, one more time. I give you what's called the deck of vertex deleted subgraphs of some graph. So I know the graph, I'm holding it right here, and one by one I give you a sequence of n vertex deleted subgraphs. So I'm going to take one vertex and I take the next vertex and I give you that deck of cards.
Are these induced subgraphs?
Not only are they induced, I mean it's all the induced subgraphs on 9 vertices for the Peterson graph. Now notice, for 9 vertices in the Peterson graph, I'm going to give you this graph 5 times. There's no method to my order. Okay? So one more time, if I give you the deck of vertex deleted subgraphs, one vertex at a time, I give you the deck, I give it to you in any order you'd like, where I give you a set of them. So if I have n, if the original graph has order n, and I remove each one of the vertices one by one, I put it back. remove it, give you the graph, put it back. Remove the next one, give you that subgraph, put it back. So I always start with the big graph, and then one by one I remove vertices. The question is, if you take a deck of, it's called a deck because you imagine that these subgraphs are on each one is on a different card. If I give you these unlabeled, can you reconstruct the original graph? Okay, this is a problem that's been around for a very long time. And he does mention it in here. So on page 68, the reconstruction conjecture. Okay, so the conjecture, it's been around for over 100 years. He gives you a little bit of the history. There are people that wrote their doctoral thesis on this. The reconstruction conjecture on top of 68, every graph of order at least 3 is reconstructible. By the way, why is it at least 3? Now think about that. I'm going to give you, I'm holding the graph. I'm holding the graph of order 2. And here's the graph. This is one of the subgraphs with one vertex removed, and this is the other. And then I'm going to give you this deck. So the problem with 2 is, how many graphs of order 2 are there? Graphs, not multigraphs, just graphs. How many graphs of order 2 vertices, are there? Now don't be fooled. What was that? There are 2. What are those 2 graphs of order 2? Don't miss this one. This is one that catches you. What are the 2 graphs of order? When I say order, that means the number of vertices. What are the 2 graphs of order 2? One edge and no edge. Okay, now imagine you've got the graph that has one edge on it. 2 vertices, 1 edge. Okay, and you're going to make a deck of cards with the single vertex removed. So first I move the right vertex, and what's left? The left vertex. Then I'm going to remove the left vertex, and what's left? The right vertex. So my deck of cards is 2 single points. Now take the graph that has no edges. 2 vertices, no edges. There's my graph. Now I remove one of the vertices. What's left? 1 vertex. I remove the other vertex, and what's left? 1 vertex. So those 2 decks are the same. So that's why in the reconstruction problem, he has to distinguish and say every graph of order, and this is not a theorem. There are a lot of people that would like it to be. The reconstruction conjecture, every graph of order at least 3 is reconstructible. And when I say reconstructible, if I give you the single vertex removed deck of subgraphs of order n-1, then you can look at that deck. You would have n cards. You can look at that deck, and you would come up with exactly 1 graph that it could be. And these are not labeled, so you don't have the advantage of a labeled graph. These are unlabeled graphs. Okay? And I want to encourage you to think about what does that mean? What is that? You might want to take, say, C5. Nah, C5 is too easy. Take this graph. Not the Peterson graph, that's too hard. It's too many vertices. Okay, so here's a graph on 5 vertices. What does the deck that you're going to get from this graph? What does the deck look like? Okay, how many cards am I going to get? 5 cards. And one card is going to look like this. Okay, that's when I remove this vertex. 1 card is going to look like that. When I remove this vertex, there's oh, sorry, I got to remove a vertex. Sorry, it helps. Okay, let's try that again. If I remove this vertex, then I'm just left with a P4. If I remove this vertex, I'm left with a P4. If I remove this vertex, I'm left with a triangle with one edge. And if I remove this vertex, I'm left with a triangle and one edge. So I have, this is my deck. P4, P4, then what do I got? A triangle with an edge, and a triangle with an edge. Okay, now this is small enough that if I give you that deck of cards, first of all, you know how many vertices the original graph has. How many, if I give you that deck of cards, a C4, two P4s, and this triangle with a little tail. So I have five cards, means the original graph has 5 vertices, and there's only one graph that has that as the deck. That's the reconstruction problem. So I don't want to disappoint you. I mean, you know, if you want to have at it, that's good. It's always fun to play with graphs. But it's only, you know, the answer to this is only known up to maybe 15 or 16 vertices. Okay, so every graph up to a certain number, the deck is, the graph is reconstructible. But the problem becomes so dense and so complicated that there's no one knows after that point. It looks so obvious. It looks so obvious. Look, I take one vertex away from this. Look, I know almost the whole structure of the graph. Why can't I reconstruct this? When you give me this deck of cards, why can't I put this together and reconstruct the original graph? Does everybody understand that? Again, we're not going to look at this again after today. He threw it in here because you should look at this and go, well, that's incredible. Incredible meaning, and this graph thing is maybe a lot harder than I realized. Okay, so I got 7 minutes. I'd like you to look at problems number on page 69, 2, 3, 4, and 5. Okay, and if you're running out of time, you might want to just jump to number 5, which is an isomorphism question. Yes? Yeah, you can. Does he use sing? No. Yeah. Same is much shorter than isomorphism.
This is like the biggest deck, like the biggest number of cards that people have
looked at? Well, people, I mean, if you put certain conditions on the graph, like you know it has a certain property, then you can get larger than 15, larger than 20. I mean, if you have certain properties on the graph, you know the graph has this property, then given the deck, you can reconstruct it. But in general, it's in the teens. Wow, it got quiet. You can talk amongst yourselves. So you have to keep going to get the graphs, right? Keep going. Oh, right there. There are the graphs. Which ones of those are isomorphic?
Das wäre
Yeah, so that means you're going to remove a set of x points. Yeah. We pretty much won't use that notation, but. By the way, if you tell me which ones are isomorphic, then you're also going to tell me which ones are not isomorphic and why.
I think A and C are isomorphic.
Yeah.
Oh,
B and
that
B
would be
Okay.
important.
A and
Yeah.
B are not isomorphic for the.
You finished all
I
of
don't
five.
think there's a 3 cycle
Okay.
Right.
in here,
I
but there
can
is a
look at
3
3.
cycle over here. You said B and D are isomorphic?
Mm.
Okay, so look at 6, but I do want to get back before I end this and go through the 4 graphs of number 5. Does everybody have the 4 graphs of number 5? Which are isomorphic, which are not isomorphic?
Is not make sure to waste time.
Yeah. I just find.
Okay, so I'm just going to tell you, the iPad, that's the way to go. Just so you can draw right on the graph. Trust me, if you ever saw my original graph theory notebook, it would be. Okay, so let's look at these 4 graphs. Can you give me a pair that are not isomorphic? Not isomorphic. A and B are not isomorphic. Why?
Because the smallest cycle is not the same.
Okay, so the small cycle is not they're not the same. There's a 3 cycle in A, and there's not a 3 cycle in B. Okay, and the next thing you're going to be looking at as we move on in chapter, what chapter are we up to? About 7. This is chapter 2. The next thing we're going to look at is, notice B has a very nice structure. B is broken up into 2 sets of vertices that are all non-adjacent. So notice the top 3 vertices are non-adjacent, the bottom 3 are not adjacent, and everything from the top goes to the bottom. Okay, those have a very special structure. Okay, and they don't contain any C3s. No 3 cycles. A contains a 3 cycle. In fact, how many 3 cycles does A contain? 2. Okay, what about C? A, that is isomorphic. It doesn't look isomorphic. It doesn't look it. Okay, so tell me how you would show me that it's isomorphic. By the way, both A and C have 3 cycles. Okay, so what's my mapping? You need to show me the relationship between the vertices in A and the vertices in C, so that one set of vertices goes to one set and all edges are maintained. Okay.
So just 3 vertices of a triangle in the graph C is correspond with
Very good.
triangle in the A.
Right. Okay, so you pick whether you want the upside down triangle or the right side up triangle, or you tell me which one is upside down or right side up. So you take one of those triangles in C, and that corresponds to one of the triangles in A. The triangles in A are pretty easy to see. When you take one of the triangles out of C, what are you left with? Those 3 points also form a triangle. Okay, and now you see that those are 2 triangles that are non-adjacent, that are non-overlapping. Just like A, you have 2 triangles that are non-overlapping, and then there is an edge between one vertex in one triangle and one vertex in the other triangle. Okay? By the way, all the degree sequences, the degree sequence of all of these 4 vertices, all of these 4 graphs, what's the degree sequence? 6 threes. Okay, what about D? D is isomorphic to B, and we know it's not isomorphic to A and C because there's no triangles. There's no K3s. I call them a triangle. It's a K3. Okay, so there's no K3s in B and D. And now the mapping, so I would take the top point, and if we're counting in a clockwise direction, the top point, let's see, that would be 1, 3, 5, would be a set of 3 points that aren't adjacent, and 2, 4, and 6 would be a set of points that are non-adjacent. And just like we have in B, all the edges between 1, 3, and 5, and 2, 4, and 6 are there. Okay, is that clear? Okay, once again, there is homework that has been given on Canvas. It should have come out yesterday afternoon. Right? I'll see you, what's today? Tuesday. If we're not snowed out, I'll see you Thursday. Questions? Yes, questions. Okay. The homework.
Yeah.
What about it?
Like for this question, is that for
Right.
It does mean like all the graph for
So it starts with an end-to-end graph. What is an end-to-end graph? So that has special notation. N2N, so N vertices and 2N edges. Okay, so this graph has N vertices and 2N edges. Okay, so now what do we know about the sum of the degrees of the graph? 2 times the edges. Okay, so if it's 4 regular, I have N vertices of degree 4. So if I have 4, I add those up, N times, what do we get? No. 4N, but that's twice the number of edges. So it's N to N. Right.
Like worry about this part.
Yeah.
Yeah.
Okay. So what if all the vertices don't have degree 4?
Degree 5.
No. So that's so that there is a z. Not all the vertices have degree 5. There is a vertex that has degree 5.
But how about if you have like an order of 5, so you can't have any like vertices in the order of 5?
Okay. Then if I have order 5, and I have so that would be a 5-10 graph.
Yeah.
The only 5-10 graph is 4 regular.
So it cannot have a degree of 5.
It can't have a degree of 5.
Okay.
But that's only for
The symbol greater than
Yeah.
or equal.
Or equal
Right.
to. So this one cannot be fit with the order of 5.
with an order of 5.
Yeah.
But now with an order of 17, okay, you can have so if I have all 4s, then I would have 17 times 4 divided by 2, which is 34. Okay, and you would have a 17 34. Okay, but if I don't have degree 4 at every vertex, so
It can be have something else. Okay.
so that's what you're trying to prove, that at least one has a 5. But if I don't have 4s at every vertex, and I have 2n edges, then one of the vertices has to have degree. I'm giving it away. One of the vertices has to have degree less than I'll get it. Less than 4, and therefore, if one vertex has degree less than 4, and what's more than 4?
So I'm just worried about if you have the order of 5, how you can find this group.
Okay, so if you have a 4 regular graph on 5 vertices,
Yeah.
a 4 regular graph on 5 vertices, you can't have any.
Okay.
So you don't even address it in the.
You don't even.
Okay. So I just
that can't
put this
happen.
part when it's
Right.
older.
Right. So yes. So it says the greater than or equal to 5.
Yeah.
But in fact, it can't happen in 5. But you should look at 6.
Okay.
And 6 and larger.
Oh yeah.
Okay.
That's my problem.
Okay.
Is that all?
Yeah.